Hello, my name is Ronan Keriel and I work at the Xilinx Research Labs, and I'm currently the editor of the Khronos SYCL standard specification. I'm going to talk to you about triSYCL, which is an open source C++20 based SYCL implementation. So triSYCL is one of the current SYCL implementation available. So the SYCL standard started around 2011 as a high-level model for OpenCL inside Khronos. And in 2014, triSYCL started at AMD, the Performance Application Engineering, to try understanding what was SYCL and how we could use it. So since then, I moved to Xilinx, and now triSYCL is mainly backed by Xilinx. The main target for triSYCL is the CPU first. So it's a pure C++ library providing the SYCL host device that use only C++ classes to emulate hardware features without requiring a real device compiler. But it's a good opportunity also to experiment to new ISO C++ features. And in the SYCL history, so Compute CPP wasn't actually still the strong production implementation, but it is a closed source. So in order to bootstrap the ecosystem, we thought it was good to have an open source implementation to back up the open standard SYCL. So in that sense, triSYCL helped the development of the ecosystem and also some other implementation, allowing them for quicker prototyping and try some extensions. So that's why now we have several other implementation. In 2017, we made a prototype to target our Xilinx FPGAs by developing a Clang LLVM-based device compiler for our Xilinx OpenCL stack. Interestingly, Intel announced that they were working on open sourcing their implementation of SYCL, which is the base of their one API DPC++. And since it was quite more robust than our minimalistic triSYCL device compiler, we decided to merge our effort and to recycle the Clang LLVM device compiler from Intel into our development. But we still reuse our own LLVM passes from triSYCL. So we participate to the public code review on the upstreaming implementation from Intel. And we also reuse our triSYCL C++ runtime in our own oncoming implementation of triSYCL for the Versal ACAP I will describe in another presentation. So triSYCL, it's an incomplete implementation of SYCL 1.2.1 plus some extension for some deprecated standard version. It's a clean room open source implementation, which is C++20 with a header-only templated class. In that way, it's simpler to integrate in existing projects. And it's modern C++ because it's make easier to implement and to experiment in an easy way. And it's also, it improves the usability for the end user SYCL programmer by giving language shortcuts. And as a side effect, we can also able to give some feedback to ISO C++. So in all this project, we try to fight back the not invented here or not written here syndromes. So we relied on all the libraries available, so relying also on OpenMP, TBB, and StudThread for efficient CPU execution. We rely a lot of Boost libraries, for example, for the OpenCL interaction. And at the end, this project also was used to help the Khronos group to refine the SYCL standard and also some other standard. But because nowadays language are so complex that it's almost impossible to define them without implementing. So in SYCL, we have an OpenCL interoperability mode. And in triSYCL, it is implemented with Boost Compute. And the interesting part is that it allows to reuse existing OpenCL C kernel in a nice SYCL way. For example, you do not need to develop all the usual OpenCL host API boilerplate to handle communication and things like that. So the SYCL API provide you basically communication and computation overlap for free. So in that way, this SYCL is just a very nice way to simplify OpenCL programming. And relying or recycling existing OpenCL kernels is also very useful in the FPGA world, where you have existing kernel that can also return in some RTL language, such as Verilog or VHDL, or you can also use some specific C++ extension for FPGAs. And you can recycle these kernels in the OpenCL framework, and then at the end you can use them directly from the SYCL framework in a simpler way. So you can access to a lot of libraries directly optimized from the vendors in that way. Even to access some specific hardware you have on FPGAs, for example, high-speed Ethernet. And that's how at some point we had a TensorFlow SYCL where you were able to execute directly some FPGA kernel from it. So the current architecture of the implementation is that, so you start from an existing SYCL program, and in the simple case where you just want to run this on CPU, you just use your usual host compiler and you just include the SYCL runtime, and then you will just have a normal host executable using, for example, OpenMP or TBB to run in a faster way on CPU. More interesting is that when you want to target a device, then you need the Clang LLVM device compiler from triSYCL that will extract, for example, the kernel part of the program, and will generate some LLVM IR with some decoration. That's what we call the SPI de facto. And from that, you can target your OpenCL-like device compiler backend that will generate some kernel binaries. And the host part is also compiled by the same kernel device compiler that will do the opposite work just by selecting all the non-kernel parts and add the glue logic to the final binaries to be able to execute some kernels generated by the device compiler for the device. What is the we have a useful extension in very simple one in triSYCL, which is that we can have a configurable SYCL namespace, because in some cases, it's very useful to combine different versions of SYCL in the same program. So we have the normal bound include that when you use it, will declare a triSYCL in the normal CL SYCL namespace. But if you want to have the triSYCL implementation side, then you can use this way to include the headers, and then it will declare everything in triSYCL. So that means that it leaves a room free for some other implementation to coexist with triSYCL. And for the lazy people, we have this header. When you include it, then you just have to use a SYCL namespace, sparing 4 characters. So if you're interested about triSYCL, you can look online for it. The open source version for our Xilinx Versal ACAP is not ready yet, so it will be open sourced later. Stay tuned. So to conclude on triSYCL, it's not a product to be used by normal SYCL programmers in the sense that it's an incomplete implementation, and there are fortunately many other SYCL implementation available today. So it's more like a research project to experiment on future SYCL version, on some extensions, on some new architectures ongoing, and to also experiment on some future C++ versions. But triSYCL has a simple architecture using the latest C++. And this simple architecture allows simpler interacting with some other implementation, because at the end, on a real target, you will have to handle with a wide variety of accelerators. So probably you will need collaboration of several SYCL versions to address everything. But since it's a pure C++, then you can build some other abstraction for any kind of devices, and that's what I will present in another presentation. And a nice side effect of pure C++ triSYCL is that you can use a host fallback mode to emulate your target and to debug on the CPU some kind of hardware features and basically co-design on your CPU just for free. And also triSYCL is independent from OpenCL with the concept of various backends. For example, we can target OpenCL. That's what we do when we use our Xilinx FPGA compiler flow, but we can also use a non-OpenCL flow when we target our Versal ACAP. So to finish, I think that triSYCL contributed to the good open source collaboration we have now across the SYCL community, and so that's why it's important to have open source implementation for open source standard. That's it. If you have some question, you can probably ask them online. Thank you for your time.